Let's check out some of the common architecting considerations when looking to implement infrastructure and configuration as code models. Firstly, there's modularization. So how the various components that define your environment are structured or referenced, such as text files, definitions, scripts, etc., can be important. Over time, as your applications and environments change and complexity increases, it can become more difficult to manage, maintain, or troubleshoot your automation files. For small to medium solutions with small teams, having single files to define your application resources and configuration can be fine and may be easier to understand and maintain. It's possible to see all the resources and values in a single file, so there can be benefits to this scenario in certain situations. However, for advanced or more complex scenarios, breaking your automation resources into their constituent parts is of major benefit. This can be referred to as modularization, or modularizing your automation assets into their component parts, which collectively define the environment and configuration for your application. Some of the benefits of modularization include: it's easier to reuse components across different scenarios, easier to manage and maintain your code, and it's easier to extend and add to your existing infrastructure definitions. Now let's look at imperative versus declarative models for automation. There are a few types of approaches to implementing infrastructure and configuration as code which you can adopt. Two of the main methods of approach are declarative. The declarative approach states what the final state should be, without defining how that final state should be achieved. Imperative. In the imperative approach, we define what the final state needs to be, but also include how to achieve that final state. The declarative approach abstracts away the methodology of how a state is achieved, and as such, it can be easier to read and understand what is being done, as well as making it easier to write and define. A declarative approach would generally be a preferred option for ease of use. Azure Resource Manager templates would be an example of an automation file using a declarative approach. Now let's look at idempotency. Idempotence is a mathematical term that can be used in the context of infrastructure and configuration as code, where it is the ability to apply one or more operations against a resource, resulting in the same outcome. In essence, if you apply a deployment to a set of resources 1,000 times, you will end up with the same result after each application of the script or template. Idempotency can be achieved in two ways: automatically configuring and reconfiguring an existing set of resources, or discarding the existing resources and recreating a fresh environment. So using an immutable infrastructure model, where infrastructure is not modified after it is deployed. When defining infrastructure and configuration as code, it would be best practice to build those scripts and templates in such a way as to embrace idempotency. Then there's technical debt. Technical debt is the set of problems in a development effort that make progress on customer value inefficient or costly. It creates unplanned work that blocks progress. It can start small and grow significantly over time through rushed changes and lack of context and discipline. It can also materialize out of nowhere, even for a project regarded as clean, because of changes in project circumstances. Technical debt includes anything the team must do to deploy production quality code and keep it running in production. Examples of technical debt can be bugs, accessibility, changing technologies or versions which are not accounted for as part of your dev process. You can think of technical debt in loose terms as the taking of a shortcut, be it intended or unintended. Technical debt is not necessarily eliminated, rather it is managed. Some considerations when managing technical debt include understanding and identifying the debt and where it is located in the code, as well as evaluating the cost to fix it. There are tools that can be used to help with this. Putting policies in place focused on preventing debt from getting worse and managing it down, such as allowing for the periodic updates of Resource Manager templates for new API versions, and doing that as part of your general development work. Tracking debt over time to ensure it's trending down in the right direction, and meeting defined policies. Prioritizing debt along with new application features and desired functionality. And finally, let's look at configuration drift. Configuration drift is the process whereby a set of resources change their state over time, from what was the original state in which they were deployed. Over time, each environment may become a snowflake or a unique configuration that cannot be reproduced automatically. With snowflakes, administration and maintenance of infrastructure involves manual processes which are hard to track and contribute to errors. Configuration drift may also introduce security vulnerabilities into your environments. For example, ports being opened that were intended to be closed, updates, security patches not being applied consistently across environments, or software installed that does not meet your compliance requirements. It can be difficult to completely eliminate configuration drift, but there are many ways you can manage it in your environments using configuration management tools and products such as Windows PowerShell Desired State Configuration, which is a management platform in PowerShell allowing you to manage and enforce resource configurations. Azure Policy, which is an Azure service that enforces policies and compliance standards for Azure resources. There are also many other non-Microsoft solutions that can be integrated with Microsoft Azure to help deal with configuration drift.